right, so in this lesson, we are going to be expanding a couple things, and then we're going to be looking at applied problems. So we're going to work our expanding and condensing again, and some more applied problems. So in lesson 4, I want you to go ahead and try this warm up on your own to see if you can expand the problems for me. So go ahead and pause the video, try the warm up, and then I'll kind of throw the answers up here. All right, so here are your answers for them. So number 1, I brought the power. I separated them using the plus sign, and then I brought the powers forward. Okay, number 2, I separated the division first, and then I started moving the power in the back forward, so that 4 forward. I separated the 5 and the y to the 6 power. Okay, because remember, when you're expanding logarithms, you only want one single thing behind it, right? You don't want any exponents, you just want a single variable or a single number, and that is what a fully expanded logarithm looks like. Okay, when you're condensing, you want only a single log left. Okay, and then you can only condense when the logs are the same. So notice I had to bump those powers back first before I went ahead and combined those logs. Okay, another way you could write this is you could have had, since they both have the same exponent, you could have written that squared on the outside if you wanted to as well. Okay, so a decibel is a unit used to measure the loudness of sound. The formula for the loudness of a sound is given by this, where dB is the decimal level. So this is decibel level. Oops, decibel. Okay. The quantity is the intensity of the threshold of sound. So this is intensity of threshold. Okay, a sound that can barely be perceived. The quantity I is the number of times more intense a sound is than a threshold. So I is the number of times more intense than the threshold sound. So the sound in a quiet library is about 100 times as intense as the threshold sound, or I is equal to 1,000 I sub O. Calculate the decibel level of a quiet library. Okay, so we need to kind of figure out where is everything going in this equation here. So take a second here and try to mentally think where everything is going to go. Okay, so if I've got, I calculate the decibel level of the quiet library, so I don't know what my dB is because that stands for my decibel. So I've got 10 log. It tells me my number of times, 1,000 times as intense. Okay, so when I go to plug it in, I'm going to have 1,000 over I sub O. That's like what it's telling me over the intensity. Okay, if I went ahead and simplified this, then I could cancel those out. So my and equal to 10 log of 1,000. Okay, so we can go ahead and type this into our calculator then. So if you're using change of base, you can use change of base. All right, so you do, if you're going the change of base route, you have that 10 in the front. All right, so I would have log of 1,000 divided by log of 10, because remember there is a base 10 that we don't see. Okay, so you would go ahead and type this in your calculator, and we should get 30. If you have that math log base button, you can also get the decibel level to be 30 as well. All right, so the sound of a traffic on a city street is calculated to be 500 million times as intense. So that just told me where I'm shoving it. Okay, as the threshold sounds, calculate the decibel level for the city. Okay, so dB is equal to 10 log. It is now 500 million times, okay, that decimal sound. All right. All right, so then we have our dB is equal to 10 log of 500 million. Okay, so you can get your change of base, log of 500 million divided by log of 10, and then multiply that times 10. Okay, we should be getting 87 for our decibel level. Okay, so now it says the sound of a crying baby registers at a decibel level. So 115 is equal to. how many times more intense is the sound than the threshold sound? Okay, so then I've got my 10 log of I divided by IO. So if I'm trying to get that IO over IO by itself, this is a multiplication of 10, so I'm going to divide by 10 to get 11.5. Okay, I can't divide by log, so if I'm stuck, I convert to its opposite form to get that I by IO by itself. Okay, so it is a base 10, so I'm going to do my swirly. So I've got 10 to the 11.5 is equal to that intensity of the threshold sounds. So you're just going to type in 10 to the 11.5 in your calculator. Okay, and it's going to be a pretty large number. It is in scientific notation. Okay, so while most medications have guidelines for dosage amounts, doctors must also determine the amount of time a medication will remain in the patient's body before it is metabolized when they write prescriptions. The amount of medicine remaining in a patient's body can be predicted by this formula, where T is the time in hours. So T is time in hours. Okay, since the medicine was administered. Okay, since the medicine was administered. C is the current amount of medicine remaining. Current amount of medicine remaining in the patient's body in milligrams, as A is the original dose of medicine in milligrams, and R is the rate it is metabolizing or breaking down. Rate it breaks down. Okay, so I know what everything is. So it says a patient is given 10 milligrams of medicine, which is metabolized at a rate of 20% per hour. How long will it take for 2 milligrams of the medicine to be metabolized? Okay, so when we're plugging it in, it's saying the 2 milligrams of medicine to be metabolized. Okay, so then we are currently wanting 2. Okay, so that is going to represent my C. All right, so the amount the patient was given. Okay, so my original dose was that 10. That's going to go in for that A. So log 1 minus the rate. So remember, we have to take that 20% and change it into decimal. So my calculator recognizes it. Okay, and it says, when is that time? So we are going to go ahead and type this in our calculator. It is in base 10, so we can literally type it in. Just make sure you end your parentheses to figure out what it is. And then take your top divided by your bottom. You should get 7.2 hours to get to that 2 milligrams in my system when I start with 10. Okay, so suppose you know that 4 hours after administering a 12 milligram dose of medicine, 9 milligrams remain in the patient's body. How can you determine the rate at which the medicine metabolizes? Okay, you can solve for an unknown in a logarithmic equation by using the properties of equality and by rewriting the logarithm. The logarithmic equation as an exponential equation to isolate the variable. Okay, so if they're trying to solve for r in this situation, what they did was they multiplied this little guy over. Okay, they went ahead and typed this in their calculator to get their decimal. Alrighty, then they divided by 4 to detach it over here to get that log. Then they converted, so it is a base 10. So they did 10 to that exponent negative 0.03125 is equivalent to 1 minus r. Okay, so then what they did was they added r, or what did they do? They added this r over and subtracted the 10 over to get r by itself, to then find the rate. So then at almost 7%, it is going to have to decrease. Okay, so 6 hours after administering a 20 milligram dose of medicine, 5 milligrams remain in a patient's body. At what rate, so we're going to find the R, does the medicine metabolize? So I know it is 6 hours, so that's PT. Okay, so we are given 20 milligrams, we have 5 milligrams remaining. So we have 5 remaining out of the 20. So 1 minus the rate. So I'm going to multiply this over to the other side. So it's going to be 6 log of 1 minus R is equal to log 5 divided by 20. Okay, I'm going to divide that 6 over because it right now is being multiplied. So log of 1 minus r is equal to log of 5 divided by 20 divided by 6. So I'm going to go ahead and grab a calculator to type it in. Okay, I get negative 0.1000343. Okay, I'm going to try to keep that decimal and use it. I'm running out of space here. I need to convert to get rid of that log now. So it's a base 10. So I'm going to do 10 to that negative 0.100343 power is equal to 1 minus r. Okay, I could subtract 1, divide by negative, or I could add this r over. So it's r plus 10 to the negative 0.10043 is equal to 1. And then subtract this 10 over to the other side. Okay, so we'd have r is equal to 1 minus that 10 to the negative 0.1003433319. Okay, so then if you go ahead and type that into your calculator, we should be getting, okay, 0.206, so almost 21%. Okay, so that's almost 21% that it's decreasing by. All right, so my last question in here. A patient is undergoing an 8-hour surgery. If 4 milligrams of medicine remain in the patient's body at the end of the surgery, and the medicine is metabolizing at a 15% per hour rate, how much medicine should we put in the person? Okay, so I've got an 8-hour surgery. Okay, we have 4 milligrams. I don't know how many I need to insert. And we're decreasing by a rate of 15%. Okay, so what I'm going to do is still multiply that over. So I'm going to shove the 8 in the front so that it doesn't get confusing with it sitting behind it. Okay, let's go ahead and find that decimal that's on that left side to make it easier. So I'm going to type in 8 log of 1 minus 0.15 negative 0.0525 is equal to log of 4 divided by x. Remember, if I'm moving to the other form, I'm stuck. I can't get rid of anything else, so I'm going to change form. So 10 to that negative 0.0525 is equal to 4 over x. Okay. Easiest thing to do is multiply the x over, or you could set it up to cross multiply. So I would have 4 is equal to x times that 10 to the negative 0.0525. So it's multiply, so I'm going to end up dividing it. To get rid of it. Okay, so when I divide it, I should get about 14.68 milligrams that I would need to be putting into his system to decrease it to that specific rate and still have that same amount left. Right? So solve each logarithmic equation using 2 different methods. Okay, so we're going to be logging both sides, and then we're also going to be doing a change of base. Or we're using, first we write as an exponential equation, okay, and then we are going to be using change of base. My exponential equation, if I do my swirly, I have 5 to the 3.1 is equal to x. All right, this one we can just type in our calculator, so 5 to the 3.1. I've got x to b, I'm rounding, so I have those little squigglies, which means equivalent. All right, the other one says first apply the change of base formula, then solve for x. All right, so I could do my change of base formula. So I would be doing log of x divided by log of 5 is equal to 3.1. Okay, so I can multiply him over. So I have log of x is equal to 3.1 times log of 5. Okay, so 3.1 log of 5 gets me to 2.166807013. And then we can convert. So this is a base 10. So I do 10 to that power. And we should get the same answer. So 146.83, same answer. Okay, so my next one here, exponent is unknown, so I'm going to do this really. 8 to the x is equal to 145. Okay, I'm going to see if 2 to some power can get me to 145. And it doesn't. Okay, so in this situation, what I would do is do my change of base, or I could log both sides. So in this one, it's going to be a decimal. I can't get the bases to be the same. So what I can do is do logging of both sides if I wanted to. So I could log and log. We practiced this a couple classes ago. Okay, then I bring that forward. Divide by log of 8. And then you're going to see that change of base appearing. Okay, so when you do this, log of 145 divided by log of 8, you get about 2.3933. Okay, I could go into change of base right away. So log of 145 divided by log of 8, and it will give me the same answer. So notice that certain ways, some things are a lot quicker. Okay, this next one, I have x to the 6.7 is equal to 24. So again, if I wanted to, I could log both sides. 6.7. What I could actually do is change it into his fraction and do the reciprocal to both sides. So if I wanted to, I would type in 6.7 in my calculator, press enter, and then do my math frac. It's 67 over 10. So if I wanted to get rid of it, I would do the reciprocal to the other side. So this was just one way you could do it. So 24 to the 10 divided by 67, which will be 1.6069. Okay, another way we could go into our change of base. So log of 24 divided by log of x is equal to 6.7. Cross multiply, so log of x times 6.7 is equal to log of 24. Okay, divide by 6.7. So log of 24 divided by 6.7 is 0.20600, and then we would still have to convert. So 10 to that 0.200 or 0600 is equal to x. Same answer. So notice which way was a little bit faster. Okay, trying to just get rid of that exponent was a little bit faster than going the full change of base route. Okay, so consider the position of the unknown for each logarithmic equation in question 1. Circle your preferred method for solving and explain your choice. So this is going to be kind of a you answer. Just circle which ones you thought were better and then state why. Okay, when might it be more efficient to solve a simple logarithm by using its exponential form for number 3? And when might it be more efficient to solve a simple logarithmic equation by using the change of base? Okay, so question 3, it's probably more efficient to solve a simple log equation by rewriting it into exponential form when the argument base is unknown or the base is unknown. For number 4, it is more efficient to solve a simple log equation by applying the change of base when the exponent is unknown. Okay, so then in question 5, we're going to circle the logarithmic equations that can be solved more efficiently when written as an exponential equation. And we're going to draw box around the equations that can be solved more efficiently by using change of base formula. So we are circling all the ones that going to exponential form would be easier, and we're going to box all the ones that change of base we think might be easier. So go ahead and circle and box what you think. Okay, so I'm going to flip these answers in here real quick on what Carnegie kind of prefers. Okay, so this one, it would be 4 to the 1/2 is equal to x plus 3. That one's pretty easy. This is x plus 2 cubed is equal to 7.1. So I would cube root and subtract 2. Okay, this one, if he was written as log base e, it would be e to the 3.8 is equal to x plus 4. Okay, this one I would have 1 minus x to the 14.7 is equal to 8. So I would do that math frac find that fraction and put them over on the other side. Okay, this one would be 10 to the 1.3 is equal to 4 minus x. So that's why solving that one would be pretty easy. This one, we have the basis and the argument. So both of these you guys can put into decimal, add 7, or subtract 2, divide by negative. Same right here. Okay, so that's kind of why exponential versus change of base might be easier for one than the other. All right, so the next step I want you to do is I want you to pause the video and go ahead and solve question 6 here in the method that you think that you would prefer. And then I'm just going to flip up the answer so that you can see it. Alrighty, so here are my last two. So I converted them both to exponential. I got them equal to 0, and then I still clicked. My negatives do actually work. If I plug this in using parentheses, it would be 9 minus 3, which would get me to 6. Okay, and negative 8 would also work when I plugged it in. So all 4 answers will actually work in this scenario.